naming something. Okay. Can you hear me on the other side?
Yes, I can.
So does it sound okay on the other side?
Sounds good so far, yep.
Chat. Okay, good. We're going to talk about translation in the next 2 weeks.
The translation functions are defined in the blocks, and then to actually figure out what happens though, whether the representations stay irreducible or split, you have to look at whether look at like the positive geometry.
Well, I mean, if you're going from Marco onto a wall, it depends if you're on the upper closure or not. If you take irreducible and allow it to stay irreducible.
Doesn't that depend on whether like the dot remains singular or not singular?
Yeah, so if it's a regular name, that's what I'm saying. You're not on a wall. It translates to a wall. Either 0 or irreducible. If you're translating off a codimension one wall, then what you do is you get a mono, which when you plug in, you have simple module class, simple module, and then you have something in between. That's called the heart. And because the impressionistic detectors are through the heart of semi-simple. We'll talk about this in a couple of weeks.
You're talking about two, because the very first result I found on Google was that they were branch over.
Yes.
I was saying, either the color or the sun.
Side,
The
yeah.
sun, you know, so that's
Undergraduate. Insert. Okay, so let's see. So let me give you a sort of general idea of what we're going to be doing in the next week or so. So today what we're going to do is we're going to work on Weyl's character formula. So I anticipate that we'll be done with Weyl's character formula sometime like on Friday. And then the next topic we're going to talk about is a topic involving what's called strong linkage. Okay. So strong linkage involves looking at the composition factors of G modules. And we want to say like which composition factors can possibly occur in certain G modules. And that's going to be governed by the action of non-action. All right, and then after that, so I think we'll probably spend sort of a week on strong language, maybe a little bit less. And then we'll spend quite a bit of time on the area of translation for algebraic systems. This is the important topic that was introduced by people at Johnson. We'll actually look at the outlook geometry and we'll actually state the results involving what happens to certain modules. So after this week, we only have 5 more weeks left. 2 more lectures. So I'm going to leave it kind of open at this point, and then I'll actually see which topics will be of relevance. We may talk about injected modules after this point. But I just want to, these are sort of basic things that are kind of important to the project or group representation. And then I'll sort of pick them up as smooth topics. Okay, any questions? All right, so let me recall a few things that we did last time. So we were looking at formal characters, and if I have a T module, then what I could do is I could define the character, the dimension of the new weight space, and then I put the placeholder E to the. And again, this is an element of the group doctrine. So then I'm going to define the Euler characteristic. So I of m as a sum bigger than or equal to 0 minus 1 to I, the character of each I. Okay, so remember what H I of M was. H I of M reduction. I write the right form for the reduction. Okay, now what do we know about this? Well, we know that HI of M is 0 for I bigger than or equal to the dimension of G mod P, which is the number of positive numbers. So because of that, this is just a finite sum. And so this is well defined. Moreover, what do we know about this? Well, M is a G, this is actually a G module. H I of M is a G module. And the character is invariant under the action of the Weyl. So this is in XMT. Okay, let me show you a picture. This is a good picture. Okay. So this picture is called Sean. So let's say we have irreducible modular lambda. So let's pick out, let's do the dominant chain. Okay, so let's pretend this is the dominant chain. This is A2. And so what do the weights look like? Well, the high weight is lambda over here. And then you know that any Weyl group, this is large, not large. So I'm just looking at the regular action of Weyl on weight spaces. So the weight spaces here look like this. Right? Plus here, 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 here. So that's kind of the outer shell. So that's like W. This is W. Just kind of go all around the shell. All right. Now the next thing to know is that Well, you can have other dominant weights inside of all lambda, but they have to be small. So the next weight is maybe a U weight. And then you have to have W translate to that, also permeated. Shell, which is inside the other shell. Okay. So, in other words, just take dominant weights for your module lambda, and then you just go around with the W action in order to get all. So you get these nice little shells. But the multiplicity is going to be different. This multiplicity is only one around the outer shell. But around the inner shell, you have multiplicity. So the multiplicity is different. Good. Now, so chi is called the Euler characteristic. And it's not a hard exercise to prove the following. So if we have a short exact sequence of E modules, short exact sequence of E modules, then Euler characteristic is additive on short exact sequences. So then IM is IM1. So in particular, if you have a module and you have a composition series for that module, then all you have to do is take the Euler characteristic on all the composition factors, and then you get the Euler characteristic for the entire module. So, okay. All right, what other properties do we have? So this is one property. Another property is if I take the tensor product of modules, then the Euler characteristic is kind of multiplicative. So it's just the character of M times the Euler characteristic of M. So let me say that V is a module for G. This follows by the tensor of M. M is a module. Okay. All right, and this is because of the tensor again. So RI induction V to G V tensor M. Only some work with the V. Okay, so what other properties do we have? Okay, so another property we have is if lambda is a dominant, if I take the Euler characteristic of lambda, this is just the character. Okay, so you only have one term in the Euler characteristic situation. And of course, this is the same thing as the character. So in a special case, when lambda is dominant P line, the Euler characteristic. Okay, so now I want to prove some facts. So let's do that next. So here's the proposition. So one, when I take the character of lambda, so I say I take the set of characters like this. Okay. So this is actually a basis for the character ring with the invariance of the W. So this is the basis for C of X. So the group algebra with the W invariance. And, second statement is the following. So if lambda is a weight, and suppose I just have a linear combination on it in a character ring. And I have to also assume that this is invariant. This is invariant over W. Okay. So then you get the following formula. If I take chi of lambda, Euler characteristic, if I take the sum over mu of a mu e to the mu, okay, so that's perfectly well defined. Then something nice happens. So this is, I just get the same coefficients here, but it turns out I can add the lambda and the mu together. So this is chi of lambda plus. So there's kind of an additivity here, but you have to assume that this element is actually W, right? To be able to sort of hold things inside the chi. All right, so let's prove this. Good exercise. So number one. All right, so first of all, so what I'm going to do is I'm going to define sim of mu. Okay, so this is the idea of this showing. So I'm going to take this mu, and then I'm going to actually take the W translates of that thing, and I'm just going to sum that. So, so this is equal to the sum of all mu in the W orbit. Okay, so just apply W and fill all this mu's, and then we just take one copy. Okay, so I think it's clear that this is invariant every day. Just going around, if you apply W, you just kind of go around. So this is going to try that. Right now, from that picture, if I take any weight, then it has to be conjugated dominantly. So since each mu in is W conjugate, dominant weight, plus, it follows that the sim is a basis for this character ring. So if I take these elements, such that mu is dominant, this is a basis for Does that make sense? You just have to, I mean, in some ways it sort of makes sense because you have to, if you have an EU in here and if you want to be part of something which is invariant, you have to take the W variance. And then you take these specific W variants inside here, and they're all really dependent. Okay, So,
So it says linearly thin, is that because it's W trying to show you the count?
yes. That's, you can, that's sort of from that. Okay, good. So, let lambda be a non-negative. So then we know that the character is certainly very. And we also know, well, using that sort of shelling idea, I can first of all pick off sim of lambda, right? So this is sim of lambda. And then I have smaller sims. So summation of mu less than lambda, I would say mu lambda. Simplicities. That's exactly the picture that I had before. And so you can see that the transition matrix is uniform number 9. So these have to be the basis. So the transition matrix is just uniform number 9. Okay. That part's done. Okay, so let's prove the next part. Any questions on this? Yes, so let's prove the next part. Number 2. So since these things are basis, so what we can do is, if I take this term over here, this thing, I can write it as a linear combination of, so I can write it as a linear combination of elements inside. So this implies that the sum of mu each of you, well, a little bit of a lie. Right? The mu is positive. No, they're not. Okay, it turns out that this is okay even if the mu's are not positive. So, okay, so this turns out to be quote the character of a G model. It might be minus the character of a G model. So, but anyway, you actually have a linear combination of these things, these all lambdas, but it could be positive. All right. So, maybe I should say something. So I'll just leave it. I'll just put this in quotes. You get the idea. So I could have like L lambda minus L mu or something like that. Okay. All right, so now let's look at this. So if I take V tensor Weyl, this has a composition series. Okay. It's a mu tensor lambda. Where, okay, so mu tensor lambda appears dimension of mu times. Okay. You just say the composition series for B is just sort of dependent on how many times the weight occurs in the weight space composition. All right, so now we're going to compute this two different ways. Okay, so let's do pi of V tensor lambda. Okay. All right. So what do we know? Well, this is sort of a G module. Okay. So we can just write this as the character of V times pi of lambda. That's from the previous formula. Right. And this is going to be, I'm going to replace this character here by this sum over here. So let's continue this on. So this is pi lambda times summation mu. All right, so that's one way to compute V tensor lambda. Now, there's another way to compute this too, and we know that on short exact sequences, the Weyl characteristic is that. So you have a composition series, so we know that you just get all these factors, just have that. Okay, so this is going to be equal to the sum of, so here are the composition factors. Okay. And then how many times are they going to appear? So this should be A, right? Okay, so the character, the weight space dimensions are equal to A and B. So I should mention that. Okay, so it's going to appear A. Right. So now we're done. Guess here I have this is equal to that. So we're good.
Something like the first formula, but that's a problem. Keep looking at the character in the comment.
Yeah. So this follows by using tensor again. Right. So because what is this going to be? So basically like RI induction of VG of V tensor. So this is a G model, so it can flow outside. Any questions? All right, good. Okay, so now we're going to proceed to analysis of Weyl's character. statement today. A little bit more work to do. Okay, so here we go. So we're going to move to Weyl character format. All right, so first of all, let me state something. So we're going to start. We're going to start some work to analyze this. All right, so suppose I take a simple root. Okay. And that is that's a t. What I want is I want lambda plus rho alpha check to be bigger than or equal to 0. Okay, so it's kind of dominant with respect to alpha. At least the inner product is bigger than or equal to -1 if I think lambda alpha check. Okay. All right, now under this condition, if you look at induction from B to P alpha, we know that H0 and R1 are related. So it turns out the character of induction from B to P alpha, okay, and this is something that comes from the section on buffer all day. This is the same thing as the character of but you know, I can't put a dominant weight here, obviously. So I have to put something which is anti-dominant. And the answer is going to be equal to S alpha alpha. All right, so another way to think about this is the characteristic of 0 is the circular. It is actually just the characteristic is circularity too. We're just working with characters. So basically, it's saying that for SL2, the Weyl module and the inducible will have the same character. This actually identifies the Weyl module. Okay, good. All right, so now what you do is you do a calculation. And I think we've done this calculation before, so I'm not going to do it again. So the first calculation is, we know what this is going to be. This is just a definition. All right, so this is the definition of the dot action with S alpha. And then when you do this calculation over here, so you take S alpha dot lambda, and you take the inner product with alpha check. Okay, so you do this calculation. And the answer is minus lambda plus rho alpha check -1. Okay, so you just unwind this definition, and this is the answer that you have. And since this is bigger than or equal to 0 here, okay, so this is going to be less than or equal to 0. So this is going to be bigger than or equal to less than or equal to -1. So S alpha dot lambda is less than or equal to -1. Okay. All right. Okay, so the next thing you know that is that because this thing is less than or equal to -1, you can use the spectral sequence that I presented in the Bott-Burrell analysis. And so by sort of the BBW analysis, if I take H I plus 1 of S alpha around it, this is equal to H I induction from S alpha. Okay, so basically the spectral sequence collapses and you get this isomorphism. Remember, the I and the 1 have to add up. So the degrees have to add up. Okay. And then when I take lambda, I get HI lambda. You can get this one. All right. So now we define something slightly different. So we can define this phi event equal to the sum for all greater than equal to 0 of minus 1 character Ri alpha to G. So this is like, instead of chi, this is phi. And the difference is that I'm not reducing from B to G anymore, I'm reducing from parallel. So it's kind of a modified version of phi. All right. So what's the point? Well, the point is that these two have the same composition factor. Okay? And so when I take the Weyl characteristics of these things, then the Weyl characteristic here. Okay. So the characters, so the characters are going to be the same because these two have the same composition factor. And so the upshot of this, so we do that. Character for these things are the same. Actually, the character for these are the same. So what does this imply? So this implies if I take the character here, which is the sum of minus 1 of these guys, right? Then I get the shift when I go up to these two. So this is going to be minus character.
Say why again, knowing that the characters, these two modules are the same, but the find rank
No, sorry, it's the Weyl characteristics. The Weyl characteristics is the function character. So the Weyl characteristics. That's, yeah, these two have the same composition factors. So the Weyl characteristics. All right, and then all right, so the upshot of this is that the Weyl characteristic on lambda is related to the early characteristic when we apply the dot action of a simple reflection on that. Now, what I did was I assumed that lambda plus rho here is bigger than or equal to 0, but then you could also argue it the other way around too. So same argument. Actually was a similar argument was rho and all right, so the upshot is that for any lambda, then this is true. Very important. Now what we can do is we can write any above element as a product of simple reflections. And then you can probably guess what the answer is. Okay, so here's the general formula. So the general formula is that take let's see, phi of w dot lambda. This is the let me use this notation, sine of w, phi of okay, now what is the sine? So the sine of w, well, you can guess what that's going to be. Well, -1 to very good. That's exactly what it is. Because, you know, in the Weyl group, everything has a certain length. It's a number, just take a reduced work, a reduced expression for W, and then you count the number of simple reflections. And that's independent of whatever reduced expression that you take. Okay, so I'll just use this sign here, -1. Okay, and then there's a note that if I take chi of 0, then W, well, then I just get 0. This is just so this is the expression. Okay. So I'll do a little bit more analysis on this, and then we'll state the last chart. Okay, so let me back up for a second and recall the lemma. Okay, so the formula of the lemma was as follows. Okay, so remember, if you take a weight, and if you take something which is in the variance, so this is the, okay, so then lemma says chi of lambda, sum mu of a e to the mu is equal to sum mu a chi of lambda. Okay, so that's what we. Now, what I want to do is I'm going to specialize this to a situation which we're going to use. So let's say that chi lambda is equal to chi of 0. So let's say lambda is equal to 0. So chi of lambda. This is special case. Now, in this special case, what happens? Well, this is e to the 0. It doesn't do anything. So we have this term over here. So we have a mu e to the mu. And that's going to be equal to a mu chi of. So this is rather nice. So there's this nice relationship between, if I just take the invariant character over here, and then I take the Euler characteristic over here, and then I just replace this by the Euler characteristic. So, okay. All right, so now I'm going to look at two properties. Okay, so now I'm going to let lambda. So the thing I want to do is I want to actually sort of extend my scales. So this is a z lattice. So let me just extend the scalars. So I just want to extend it. So you pick a z lattice. All right, so if I define a lambda as follows. So if I take W and W, and we look at sine of W times e to the W lambda. So again, we're doing the showing business, but we're actually going to take sine this. So we don't know. This is not an invariant. Remember, if I don't have a sign here, then so all we know now is that this is in C of x of t tensor q with character. All right. So now we have various properties. So the one thing we know is that when we apply a biological element to this character over here, then it's going to change by applying the sign. So if I take W prime of a lambda, that's going to be equal to the sign of W prime times. That's not hard of an exercise. You kind of see. Okay. And it has so suppose you take two of these things. So if I take a mu and a lambda, then you get something which is under the option. So the way you can see that is as follows. On this right over here. Okay, so we take W. Okay, so it's gonna. This is a product. It acts as follows: W, A mu, W. It was by the first formula, sine W sine of sine of W. And of course, when you take sine of W, sine of W squared, that's going to be 1. So that proves that. All right. So now let me state the theorem. So this theorem actually says what the pi lambda is. All right, now this actually holds for any weight, not just the dominant weight. So it says the following. So let lambda be any weight. And so we know what the Euler characteristic is. So then the Euler characteristic of lambda is going to be equal to A, this A that I present up here, lambda plus rho. Or theta rho. And then again, rho is the absolute constant. Any questions on this so far? Now, what's kind of amazing about this is that, I mean, these are actually just formal sums, right? And so we're saying that this formal sum divides those, which means that this times something is equal to this. So there's a certain divisibility going on here, which is kind of nice. Now, what's a corollary of this? So the corollary is right? Lambda b. So then we know that the character of H rho is equal to this. So we can actually compute the formal character by using this quotient. Now, before, we had talked about the dimension of these or lambda as well. So this is kind of similar to that. Sorry, I think you derived that dimension. Sure. All right. Any questions on this so far? All right. Now, I want to save the food for next time because it's going to actually involve some work. So let me just mention a few things before we go. So one of the big questions is what's a character formula for all axes? So the big question. Is K go to characteristic P. So what is the character formula? juncture, we know it for P very, very large, but in general, we don't know. Yes, we do know it in terms of what's called economic basis. So philosophically, I think we're going to answer. In practice, I think the answer is still somewhat satisfied. And as you know, notice this is actually close for the character. All the character formulas here are recursive. So no. Maybe there are not. All right, so let me just say what we'll do next time. So next time we'll have to prove this. Files, character formula. That's one thing we're going to do. And then the next time we'll also do an example. So we'll actually complete an example using the state. And we'll see how it works. And basically, the idea is the following. Let's say you take this character over here, which you don't know. So it's going to be the sum over some use, let's say. So by Weyl character formula, we multiply this on the other side. So I'm going to have this mu summation. Okay. And this is going to have to be equal to. All right. So the goal is to have to compute the coefficients. So in order to compute the coefficients, you have to use point coefficients. And then when you point coefficients, you get a bunch of linear equations. And then you solve the system equation. That's kind of we're not actually going to do that in the example. We're just going to verify that the example works. The principle, this turns out to be a linear algebra. Right. So it's doable, but it might involve lots of major complications. All right, any questions? Okay, so let's stop there.